In this lecture, we will be looking at an important aspect of NMR spectroscopy. You will be introduced to a concept called polarization transfer. I'd like to recollect some of the aspects that we have learned so far. Let's say you have an excitation pulse followed by acquisition. You remember that the observable ends up coming. Let's say you have just a single spin I. You're going to get trace of I plus to the final density matrix, which is obtained here, will be of the form exp I omega t. And in the case that you have I and S spin that couple with each other, in such a case the trace of I plus to sigma comes up as exp I omega t times cos pi j_t. We saw in the previous lecture that when this signal is Fourier transformed, you get a resonance or the Dirac delta function at plus omega and nothing at minus omega. So similarly, when you have the cosine modulation, all this ends up doing gives a signal at plus omega that is split with the j coupling of 2 pi j, and the intensity being half is to half with respect to whatever you started with. Now let's take an instance where we want to obtain a carbon-13 one-dimensional NMR spectrum. In order to achieve this, all that you have to end up doing is to simply apply an excitation pulse. We will continue to stick with a 90-degree Y pulse followed by acquisition. And you know for a fact you are going to end up getting the final solution that looks of this sort. However, I'd like to start from the equilibrium density matrix, which is going to be given by omega c times Cz. So therefore, your final trace of I plus to sigma will be given by omega c over 4. The 1 over 4 comes up because you would end up getting a cx square cy square, which is equal to 1 over 4. That's how this 1 over 4 comes up, and omega c comes from wherever you started with times exp I omega t times cos pi j_t. So therefore, you're going to end up getting a spectrum that looks like this. So you're going to have omega c by 4 times 1 over 2, so omega c by 8. Omega c by 8 will be the intensity for this, and split by 2 pi j, centered around capital omega c. So this is what we would get when you apply a simple one-dimensional NMR spectrum. But with the power of whatever we have learned in the previous class, that is the spin echo, let's try to see how things change. So we are going to be exploiting something more different, a little complicated, but gives you dividends at the end of the day. So this is the 90 Y pulse followed by tau delay, 180 degrees x, 90 degrees x, 180 degrees x, 90 degrees x. This will be the proton channel and this will be the carbon channel. And the tau, we will see, similar to the spin echo that we had seen last week, will be set to 1 over 4 JCH. So the question now what we have is that, let's say I acquire along the carbon channel. What will be the difference between a simple one-dimensional NMR spectrum and the pulse program that we are trying to implement in this case? So let's rewrite what will be the equilibrium density matrix. That is going to be given by omega h times hz plus omega c times cz. Instead of using I and S, I feel it's easy to use h and c so that one is able to understand what ends up coming. So in this case, the pulses that you apply along the proton channel will not affect any of the carbon magnetization, largely because any H operator, Hi, Cz will commute. So therefore, there will be no effect of the proton pulses on the natural carbon magnetization. However, it will have influence on this one, which we will see in a moment. So for all practical purposes, the carbon magnetization is going to only end up seeing the pulses that are applied to the carbon channel. And there is yet another piece of information that I would like to give to you right now. Generally, a 90-degree pulse results in change of coherence. Not always, we will see some examples. Meaning, let's say you start with CZ, you apply a 90-degree X or Y pulse. Let's say apply Y pulse, you're going to get CX. Order of coherence for CZ is 0, the order of coherence for CX is plus minus 1. So you're going to change the order of coherence with a 90-degree pulse. The case is same even if you end up applying a X pulse where you're going to get minus CY, that is still a plus minus 1 coherence order. Similarly, let's say you apply a pulse from Cx with a 90 degrees along Y, you're going to get minus Cz. So you started with plus minus 1 coherence and you end up going to 0. On the other hand, if you're trying to apply a 180-degree pulse, that will never change the order of coherence. Why am I detailing all this? Because that's going to help you apply this part of the pulse program on the natural magnetization of carbon in a very easy way. For instance, let's say you are along CZ and you applied a 180-degree pulse along X or Y axis, you're going to get minus CZ. Similarly, if you are along Cx and you are applying a 180-degree pulse along X axis, you are going to remain wherever you were. On the other hand, Cx on a 180-degree pulse along Y is going to be minus Cx. In all these cases, you see that the order of coherence has not changed before and after the application of the pulse. The only reason why I did not say always results is largely because you could have a case where you're along Cx and you're applying a 90-degree pulse along X axis. It will remain as Cx, so you're going to be in the same order of coherence. Of course, most often the cases that we'll be looking for would belong here, and for 180-degree pulse, it's a very easy way of application. And why do we bother about coherences? Because coherences are the ones that are observable, not polarization. So therefore, what we are able to understand here from this pulse sequence is tau delay, you're going to have omega c Cz that is present, which will commute with the density matrix, so no change will happen. The 180-degree pulse, all that it will do is to make Cz to minus Cz, followed by tau. Once again, the chemical shift Hamiltonian for carbon would be active, which will commute with Cz again, so no change will happen in this tau duration. You started with omega c Cz. The tau duration omega c Cz is going to remain omega c times Cz, followed by 180-degree pulse along the x-axis is going to make it omega Cz with a negative sign, followed by the tau duration. Once again, you have omega c Cz as the operator, so no change will happen. It will remain omega c times Cz. Then, if you are applying a 90-degree x pulse, it is going to be plus omega c Cy, and you have acquisition. If you calmly do the acquisition, you have two components there, omega c Cz and 2 pi j Cz Hz. I would like to point out an important thing here. I am still using the weak coupling approximation, largely because you are able to understand omega h minus omega c, which is, let's say, for a 400 megahertz, 400 minus 100 megahertz on carbon is going to be 300 megahertz, and the magnitude of 1jch is at best 200 hertz. So you're able to see that the chemical shift difference between proton and carbon is much greater than the J coupling evolution, which allows us to use the weak coupling approximation. When you allow the evolution to happen in the presence of chemical shift and J coupling Hamiltonian, we just saw a moment back, the solution is going to be omega c times cos pi jt. One thing that you have to remember is weighted as omega c over 4. The same result that we had gotten earlier, all we have done is to invert the polarization before we started. So there is no big difference that you end up getting here. Okay, so therefore, the natural magnetization of carbon ends up giving a spectrum that looks like this. Weighted as omega c over 8. Intensity will be omega c over 8 is to omega c over 8. The 1 by 2 comes because the single resonance gets split into 2 and therefore it becomes omega c over 8. The splitting will be 2 pi j. So now let's go back to this INEPT module. Instead of just looking at the carbon portion, now we'll look at the proton portion. So you had the initial density matrix as omega h z. You are applying a 90-degree pulse along the y-axis. It's going to make it omega h along hx. So we applied the first pulse right now. What do you have here is that evolution as a function of time, which is tau delay. And the things that operate in this region right now are omega h z and 2 pi j hzcz. This is a scalar coupling, Hamiltonian. And we just learned in the previous class that when you have a tau 180 tau module where the tau is equally set on either side of the 180-degree pulse, the chemical shift ends up getting refocused. So for all practical purposes, we do not have to evolve during this tau delay with chemical shift of proton. You may ask a question, what happens to chemical shift of carbon? You realize that it has an operator of Cz. Since Hx commutes with Cz, chemical shift of carbon also does not evolve. So during this tau duration, all that evolves is 2 pi j Hzcz. So what will be the answer? Omega h times Hx cos 2 pi j tau plus 2hycz sine 2 pi j tau. I have taken the liberty of applying this entire duration as J-coupling evolution for twice the amount of time. Tau plus tau will be 2 tau. So I have taken the liberty of doing this largely because in the lecture preceding to this one, you had seen what is the effect of scalar coupling on the spin echo module. The next step that we are going to be doing is to apply a 90-degree pulse along X for proton and 90-degree pulse along X for the carbon. But we can make our matters easy largely because we have set tau to 1 over 4j. If you realize if you set it that way, the cos part goes to 0 because it will be cos pi by 2, and the sine part becomes 1. So overall, you are not going to have the hx portion and the sine portion will go to 1. So the whole thing can be written in a much smaller form, omega h times 2 hycz. If you are applying a 90-degree pulse along x-axis when the magnetization is along y, you are going to end up getting 2 times hz with a positive sign. On the other hand, if you are having the Cz magnetization that is present or the operator that is present and you are applying a 90-degree across x, you are going to end up getting Cy with a negative sign. And just for the sake of simplicity, just like we like to have positive numbers, so we can apply this pulse along minus x-axis, just for the sake of simplicity. So now at this point, what you are able to see is that the density matrix is represented by 2Hz operator. Now this can evolve with time. Remember, right now, the time evolution as omega c Cz. Why do not we worry about omega c Hz? Because it will commute with this given operator. So that's why I am not writing. Plus 2 pi j Hzcz. So when you have this condition, since the chemical shift and the scalar coupling Hamiltonians commute, you can do one at a time. So let's do calmly one at a time. I'm not going to write omega h for the time being. So only with the chemical shift evolution, you are going to get 2 Hzcy cos of omega ct minus 2 Hzcx sine omega ct. Now you can apply duration t with 2 pi j Hzcz. This is going to be, of course, the whole multiplied by omega h. Omega h times cos omega c times t 2 Hzcy cos pi j t minus cx sine pi j t. Then minus sine omega ct. All I am doing is evolving this term right now. Previously, we have evolved this term to get whatever we want, times 2 Hz Cx cos pi jt plus Cy sin pi jt. It is very important to look at these terms here. If you do take the trace of this entire density matrix, so this is your final density matrix, and you are able to understand if you take C plus times the density matrix, you will have a component that's left which will be heads of the form Hz. So this will not be observable, so will not be this, but however you do have single quantum terms that will be observable. So now let's just write it in its full glory. What do we end up getting? So I'm just going to write whatever is pertinent, omega h times cos omega c times t, the negative sign, sin pi jt, minus sin omega c times t times sin pi jt. I missed an cx and then there will be a cy here. This is your final density matrix which is observable. Let's take a trace of C plus to sigma final right now. What will end up coming? Omega h by 4 times, of course there's a negative sign that will come due to this, exp I omega ct times sin pi jt. This is very important right now, largely because you remember from the Fourier transformation discussion, if you have a sign modulation, you will end up getting 1 over 2i delta function omega c plus pi j minus small omega minus delta function omega c minus pi j minus omega. So how will the spectrum look in this case? 0 minus omega c plus omega c. You will have a resonance when omega is capital omega c plus pi j and omega equal to omega c minus pi j. But recollect that there is a negative sign here, so your spectrum is going to look something of this sort. But you have omega h over 4. Of course, there's a minus sign. You can all multiply the entire thing by a minus 1. That doesn't make any difference. So you're going to get omega h by 8, omega h by 8 separated by 2 pi. This is an important outcome, and remember, this has come solely from the proton magnetization. This is exactly what is termed as the polarization transfer, meaning that you started from the proton polarization and you are able to observe carbon magnetization, finally coherence actually in this case. The main difference between whatever you obtain directly from carbon, let's draw that right now. So we had the spectrum that was obtained directly from carbon here. I'm just going to be invoking the same thing here. So that's going to be plus on both sides. Remember, they match. The weighting was omega c by 8, omega c by 8. So the important thing that you're going to end up getting, it will be a simple arithmetic sum of these two spectra. So you're going to end up getting something that looks like this: 0 minus omega c plus omega c. You're going to have these two signals that add with each other. So you're going to get omega h plus omega c by 8. On the other hand, in this case, it's going to be omega h minus omega c by 8. If you just give tentative numbers, what do I mean by tentative numbers? If you said omega c by 8 is equal to 1, then omega h by 8 is equal to 4. These are just relative numbers so that you can understand how the spectrum is going to look. So this is going to be 4, this is going to be 1, this is going to be 1, this is going to be minus 4. So therefore the sum and the difference will give you 5 is to minus 3. Remember, previously you had a 1 is to 1 and you're boosting it at least by 3 times to get sensitivity enhancement. Of course, people who have done NMR would realize that, oh, why don't we decouple to get a better sensitivity? Unfortunately, if you decouple, your 5 and minus 3 will destructively interfere to get just a very small gain in the intensity. But overall, what you are able to realize is that you are able to transfer the polarization from proton to carbon to benefit in a signal boost that we end up achieving. We will see in just few moments how this can still be exploited in order to get better sensitivity without the problem of having a plus and a negative resonance. The main issue if you have a plus and a minus resonance is that you could have another resonance that's plus and minus that will destructively interfere with it. Here we are just seeing one example of capital omega c, but in a real system you're going to have multiple carbons which could destructively interfere, meaning that you have a plus and a minus, and then another one could be a plus and a minus, and the resonance here would be completely missing. So therefore, INEPT, although giving you a very good sensitivity boost, might not be very applicable, and in the next module as we go forward, we will see how this can be converted. And we just learned at this point the product operator is something of the form 2hzcy. I think I put a minus sign there. So let's just add one more module to it where you have another tau 180 tau duration, where this tau duration is also 1 over 4j, 180 degree pulse, let's say along the x-axis, shouldn't matter much, and then you are acquiring along the carbon channel. Until this module, the refocusing module, is applied, you had the density matrix represented by 2hzcy. And in this case, once again, you know for a fact carbon chemical shift could evolve, but since it's a tau 180 tau module, carbon chemical shift will not evolve. Proton chemical shift omega h z will also not evolve because it commutes with this given operator. The only operator that evolves is 2 pi j h z c z. And therefore, we can actually write what is going to end up coming here as a 2 tau duration. 2 h z c y cos 2 pi j tau minus cx sine 2 pi j tau. The important thing here is that you have set tau to 1 over 4j. That immediately indicates this will go to 0 and this will go to 1. Therefore, you are only having minus cx. Remember, all this is weighted with the omega h. Right? So finally, you are going to get omega h times cx. And cx, when it evolves as a function of time with omega c cz plus 2 pi j cz hz, you will finally get an expression that looks like exp I omega c times t times cos of pi jt. And therefore, now this will give a signal which will be in phase for both. So remember, this is weighted with omega h, and therefore you're going to have both as plus. So therefore, from the proton channel you're going to get 4 and 4. From the carbon channel you're going to get 1 and 1. When you sum these together, you're going to get 5:5, which is significant sensitivity boost from where you started. And now if you decouple, what will end up happening is to get a single resonance at the sum of these two, which will be the intensity of 8. So which you would have got as an intensity of 2. And what you are able to appreciate from this fact, whatever you would have gotten as intensity of 2, you are getting intensity of 8. You are getting a 4 times boost in sensitivity that's coming from the gyromagnetic ratio of the proton. This module is called the refocused INEPT, where the first module that we ended up applying here in pink is called the INEPT module. INEPT stands for Insensitive Nuclei Enhancement by Polarization Transfer. A RINEPT is just a refocused part of INEPT. And what you are able to see here, if you apply this pulse program, of course, you can also decouple right now, which you couldn't do previously. You're going to get a boost in sensitivity. But however, there's a small caveat here. We are only talking about carbons that are attached to protons, single protons. When you have multiple protons, if you do the product operators, you have to do this multiple times. The J evolution has to be done more than once. You will see that the J delay won't be 1 over 4J anymore. On the other hand, when you have quaternary carbons that have no protons that are attached, you are not going to observe the signal. So although the refocused INEPT gives you an advantage of obtaining carbon spectrum at a boosted sensitivity, it relies on the fact that you have protons that are attached. However, the INEPT module forms an integral scheme in almost any NMR experiment that is implemented to get heteronuclear correlations. By heteronuclear correlations, I mean 1H, 13C 1H, 15N 1H, and so on, or even 13C 15N kind of correlations are done using this INEPT module, provided they share a scalar coupling delay. I hope this module helped you understand how, when you are able to use the density matrix formalism, you are able to come up with some schemes where you generate a certain polarization that helps you enhance the signal sensitivity by the more sensitive nuclei. Basically, the rich person ends up feeding the poor person. The poor comes from the fact that the gyromagnetic ratio of carbon is lower than that of the proton. So therefore, you exploit the fact that the proton has higher polarization, which is taken in by the carbon to give a better sensitivity.